Senior Director of Product Marketing here, but hopefully you won't let it fool you. I was an engineer myself and like to think I'm still a developer at heart. My passion at work has generally been around distributed systems and databases. And then over the last few years, as I'm sure many of us have, my interest has pivoted to AI, a little more specifically around large language models and how they're used. For those of you who may be new to Snorkel or joining us for the first time, I just wanted to provide a very brief introduction to Snorkel Flow. It's an AI data development platform. So what does that mean? In a nutshell, this platform helps enterprises, accelerate and scale data labeling, right? With the ultimate goal of curating very high quality training data. And certainly distillation is kind of one means of that, which we're going to talk about today. But if we think about some of the features involved, some of the mechanics, part of it is streamlining collaboration with SMEs, right? Whether they're doing some manual annotation or they're adding tags and comments, but it's important to get SME input and feedback in this process. Pragmatic data labeling is really the magic, right? Instead of having SMEs spend hours or months, manually labeling everything, we have this notion of labeling functions, which allows us to, label an entire data set at once based on SME logic. There's built-in error analysis tools, LLM evaluation, right? This is all kind of part of an iterative development lifecycle. Then, of course, once you've reached your accuracy requirements, you can train and deploy that model. So this is a complete platform for developing the data that you need to train models, right, to be more accurate and then ultimately deploy those. But that's enough of Snorkel Flow. Let's jump into the primary topic here today, distillation. I wanted to first start with the context, right? I mean, the idea is, this should come as no surprise to anyone, we want fast, accurate responses from our models, and we want to pay as little as possible in inference costs. Whether that means you're paying, by token to a third party who's hosting a model, or you're paying for GPUs if you're self-hosting it. Regardless of the path, we want to have our cake and eat it too. The challenge here is, I'm sure everyone's seen if we're watching the news and seeing new models coming out on a regular basis, is they're getting bigger. They're bigger and bigger, bigger. Certainly that is fantastic in the sense of what they're capable of. The generalization, it's so broad, right? There's so many use cases for LLMs now. And certainly when you look at, few shot or even zero shot prompting, they're getting better and better at it. The challenge is that as those models get bigger, they have to perform exponentially more calculations and require significantly more hardware. The very biggest models aren't even going to fit on a single GPU, no matter how big that GPU is. And when that happens, there's kind of two side effects. One, the obvious one is the cost, right? If you have to invest heavily in GPUs, or you're paying a high fee for millions of tokens, those are going to add up very quickly. The other side effect that sometimes we see, sometimes we don't, is the response latency, right? Smaller models, while less knowledgeable and less capable, can respond very quickly, and we like that. Very large models, especially if they're running on constrained hardware, take longer to respond, and that can be a little bit frustrating. And so the idea is, how do we solve this? How do we have our cake and eat it too? It's really around model compression, right? The idea is, no matter how big these models are, how can we shrink them and make them smaller, right? And by doing so, we want to retain as much of the capabilities and the skills and the knowledge that they have, but still kind of reduce that footprint so it's more manageable. There's a handful of techniques for that. We don't have time to go into them today, but things like pruning and quantization in particular are just methods of removing what we believe are the unnecessary or less important parts of the model, right, to get them smaller. However, when we think about foundation models and frontier models, specifically, in this slide, I was thinking about benchmarks. They're very broad, right, from writing code to performing calculus, using APIs of different tools and services. But in practice, depending on what you're trying to do, you might only need one of those skills, right? If I'm building a co-pilot, or an assistant that helps, for example, customer service representatives interact with customers and answer their questions, I probably want those reasoning capabilities, right? I obviously don't need a large language model capable of writing code, right? That's not what I'm trying to accomplish. So then we kind of rethink it a little bit and say, well, we want fast, accurate responses. Of course, we want our low inference cost, but typically in the enterprise space, we also have this notion of task specialization, right? We're not trying to build a generalized model for the world to do ask me anything, right? I'm trying to solve a specific business problem. And you can often pair that with, I have, ideally, a healthy amount of unlabeled data available to me. So if you're checking those two boxes, distillation is the recommended approach. And that, of course, is the topic today. So we're going to kind of dive deeper into that now. But when done successfully, we get both of these things, right? We have fast responses, we have low inference cost. And while we haven't retained 100% of the knowledge of the model, we have retained the task-specific capabilities, right? So the knowledge and skills that are necessary to solve our problem, we've retained those. I wanted to highlight, just two places where we've seen this in practice. One of the earliest examples was Stanford's Alpaca. So essentially, they took the latest GPT-3 model that was available, and they generated, you can see 52,000 QA pairs, right? So kind of using it for self-instruct, generating this training data. Then they took those QA pairs and they used it to train a Llama 7B model. What's fascinating about this and impactful is you see there on the left, less than 2 months and less than $600 was spent. But when they were finished, they ended up with a model that was comparable to GPT 3.5. So again, they have a smaller model. It's going to have lower inference cost, but it's meeting our accuracy and latency requirements. Fast forward a little bit, and NVIDIA just published a research paper not too long ago. I'm not going to do it justice here, so I encourage everyone to check it out. But the summary is this notion of, instead of pre-training a variety of models in a family, from very small to very big, what if we simply started by, pre-training our large model? In this case, it's Nemotron 15B, and then chose to both prune and then distill the knowledge from the teacher to create a smaller one. And that's Minitron 8B. And then, of course, they did it again, right? We're going to prune Minitron 8B down into Minitron 4B, and then we will use distillation to retrain that model. The key takeaway here is that red line in the graph. So you can see the original Nemotron 8B, cost to train, and then kind of on the left side, the accuracy, what is it, maybe, 55% in this benchmark. A similar size model generated through distillation ended up being significantly less expensive to train and delivered much higher accuracy. Even that Minitron 4B model was delivering higher accuracy than the original Nemotron 8B model. So this is an example kind of more recently in the commercial space where people are actively applying distillation